So for this segment, we're going to introduce the multiplicative weights algorithm in a non-private setting. And this might seem unrelated at first, but don't worry, we'll bring it all back in the third segment. So the setting is as follows. You have a set of n experts, or so-called experts, and they claim they have some arcane knowledge which allows them to predict the future. They're somehow all magical, and they can all see what the future is. But the thing is, all of them are lying except for one of them. Only one truly knows what the future is, and everyone else is just making stuff up. Of course, this seems like a great, even if there's only one person in the set who's very knowledgeable, it seems like, wow, this is a great power. Can I use this to do something useful? So as a kind of example, you can imagine you want to learn how to, you want to use their power to invest in the stock market naturally. And every day, we'll describe the setting. Every day, so we're going to have a bunch of time steps, t sort of equals 1 up to some t. And every day t starts by each expert giving you a prediction. So each day, each day, this is like expert I prediction. About what's going to happen. Is the stock market going to go up or going to go down? And so this is equal to either U or D, up or down. So each of them gives you their own prediction, and then you have to make your own prediction based on this. You or your algorithm. U or D again. And then the true signal of the day is revealed. So S to the T. So like the stock market either goes up or down. And then based on this, you either like you might make a mistake. Let me call what are we going to call your prediction? Let's call this just P of T. What your prediction is, and what happens is you're of course trying to predict what actually happened for the day, and you say if P to the T, if your prediction on the Tth time step is not equal to the true signal on the Tth step, then this is a mistake. So hopefully the setting's clear. There's a bunch of experts who all give you predictions. They all might be phony, answering arbitrarily, except only one person will always match the true signal for the day. And the question is, how can you make as few mistakes as possible? Your goal is really to try to match the true signal as many days as possible from t equals 1 to capital T. How well can we do this? Kind of seems a little bit impossible because you have no idea who this person is. How can you tell who's telling the truth and who's lying? Well, there's fortunately a very simple algorithm which always makes at most log n mistakes. Now that I've told you log n, it could be interesting if you try pausing and seeing if you can figure out what exactly this algorithm is that makes log n mistakes. Kind of gives you a hint based on the fact that it's log n. So try pausing and maybe figuring it out yourself before you proceed. But the algorithm which does this is very simple to describe. In particular, every day we predict in concordance with the majority of the experts, and at the end of each day, we eliminate everyone who was wrong. So that seems natural. If somebody ever makes a mistake, then they couldn't be the expert who actually knows the future. So you might as well remove them, and always predicting with the majority seems like a reasonable thing to do. So let's see this algorithm written a bit more formally. So we can see we set our initial set starting is going to be, we're going to consider all the experts who are still alive to be the whole set of 1 through n. And for each time step, we do the following. We're going to define S sub U to the T to be the set of experts who predict U. And similarly, you let S sub D to the T be the set of experts who pick D. And you predict with the majority. If this set is bigger than this one, then you predict U. Otherwise, you predict D. And then you can see that we update the set S to be equal to essentially the set of people who predicted correctly. You can see this ST, which is the true signal. And the claim about this algorithm is that it makes at most log n mistakes. It's not too hard to see. This is the simplest analysis we'll do today. But, and if I wanted to describe how the analysis worked in a sentence, it would be the following. Either half the experts are right and we don't make a mistake, or half the experts are wrong and therefore we get rid of a lot of them. We get rid of at least half of them. More precisely, suppose we make a mistake at time t. At some time t, then we have the following property. We have that size of s to the t plus 1. This is going to be upper bounded by the size of s to the t divided by 2. Like I said, the reason is just because, this meant that at least half the people were wrong, so we get rid of at least half the people. And, it's a decrease in the size. So since we start with n experts, this implies that, the number of mistakes we can make, the number of times you can have it is at most log n times. And I mean, you can never go below one expert because they'll always make the right answer. So okay, this is cool. What we did was we had our algorithm made we made log n mistakes at most, and the best algorithm made 0 mistakes. The best expert in retrospect made 0 mistakes. So this is called our regret. So this is an important term. The regret of an algorithm is, the difference between, in this sort of online setting, this is called the online setting, where we have a bunch of choices in a row. So this is kind of the error of the real algorithm. So how our algorithm does in practice, minus, the error of the best option in hindsight. And importantly, it's the best single expert. For example, you could imagine that if there's always at least one of the experts who always, okay, I guess it's not going to make that big a deal here, but, this is the error that our algorithm makes, and this is the error of this individual who is all-knowing. So in this case, we can see the regret is bounded by log n here. So that's the simplest case. This is a bit too simple in particular. Let's make it a little bit harder. In this, we had some knowledge, or the fact that there's at least one expert who always knew the future. But this is kind of too much to ask for in general. Maybe you don't have an expert who always knows the future. Maybe you just have someone who's like pretty good at predicting and can guess correctly, but is not going to know every day so correctly. So this motivates the case where we don't have a perfect expert. Now we have a best expert. So the best expert is going to be a bit different. Now we say, the best expert makes at most, or let's say makes exactly opt mistakes, where opt is some, optimum number of errors we can make. So before it could correspond to opt equals 0, but now we're just going to consider a more general value for opt. So it's not hard to see that the above strategy, if you just try to do it naively, would not work for opt being greater than 0. Why is that? Think about it for a sec. Well, you could imagine if in the first round, the best expert who just makes a mistake on, say, the first time, and then never again, if they make a mistake on the first round and then everyone else predicts correctly on that first round, then you would make a mistake with you would eliminate the best expert in the first round, and then maybe everyone else predicts incorrectly forever after that. So as you can see here, this is kind of like a very irrevocable decision if you chose to leave this best expert out, or if you chose to immediately just get rid of them. So what we're going to do is, instead of making this very hard, irrevocable decision, we're going to try a softer strategy. Instead of just kicking them out immediately, we're going to trust their opinion less. If somebody starts telling you a wrong opinion once, then maybe you'll just discount them a bit. But if somebody repeatedly makes a lot of mistakes in a row or over their timeline, then you're going to just stop trusting them altogether. So essentially what you're going to do is divide, if you have a weight for each individual, and you're going to divide their weight by 2 each time you make a mistake, each time they make a mistake rather. So this is kind of like a softer version than before, because before what we did was multiply each person's weight by, multiply each person's weight by 0 when they made a mistake. But here we're going to try something a bit bigger and just multiply it by 1/2. It's kind of a softer like discounting. And also the question is, now we're not just going to go with the majority opinion, we're going to go with the weighted majority. So let's just see, like down weighting instead of eliminating something. And the other thing is the weighted majority. Rather than the just strict majority in terms of size. So these will help us, pick out this best expert much easier, better than before at least, for the setting. And in particular, this is the type of theorem we're going to get. I claim that there's an algorithm that makes at most 2.4 times opt plus log n mistakes. Yeah, note that before, like I said, what does this leave to be desired? We'll go on to the algorithm in a second, analyze it, but what does this leave to be desired? Well, there's 2 things. So okay, we incurred some sort of like opt here, but that's okay, we can't hope to do better than opt. But what is not great is that we have this sort of ugly constant in front of opt. What we would like is for, the algorithm solution minus opt to be like less than, say, log n. But you can see here, that's not the case. It'll have like this 1.4 opt. So it's not the greatest in the sense we would like it to be additively competitive with the best solution, but it's not here. Yeah, but nonetheless, it's still pretty good because it's better. It's still in some sense competitive with the best possible solution we could do. And we're going to see how this gives us some nice ideas, which we'll be able to refine into a better algorithm in the future. Okay, so let's take a look at the algorithm. It's again not going to be too hard to analyze, but a little bit harder than before. So let's see. Initially, we start with each individual's weight. Each individual is going to start with a weight of 1, because we trust them all sort of equally at the beginning. But what we're going to do is, in each time step, what we're going to do is we sum up the weight of everyone who predicts U. And you sum up the weight of everyone who predicts D, and let these be the total weights of these sets. And you can see that if the total weight of the people who predicted U is greater than the total weight of the people who predicted D, then we will follow the majority rule. We pick U if the majority says that, otherwise we predict D. So this is kind of a softer way of, again, doing what we did before, where instead of having we picked whatever the majority picked, we picked now a weighted majority. And so we're going to incur whatever loss we incur, if we make a mistake. But the last and important thing is the fact that, for everyone who's wrong, anyone whose prediction, any expert whose prediction does not equal the true signal, then you set their new weight to be 1/2 of their old weight. So yeah, just rescale it down rather than totally eliminating them, and take a weighted majority. That's it. Okay, the analysis for this is actually, it's harder than before, I'll say, but it's not too bad, and I think it's kind of nice in the sense that, what we do is we take a nice sort of quantity, we upper bound it and we lower bound it, and putting those 2 bounds together gives us the regret bound that we're looking for. So what I want to say is let WT be the total weight at the end of the process. So this is going to be, if you sum up every expert's weight at the end, I equals 1 to n, then this is the total weight at the end. And we're going to upper and lower bound this quantity to relate opt and the number of mistakes we make. So let's let m equal the number of mistakes that the algorithm makes. So this is the bound, and this is what we're going to try to, this is the quantity we're going to try to bound. So All right, let's upper bound and lower bound this quantity, and then we're going to relate those upper and lower bounds together. So let's start with the lower bound. So the lower bound is the following. So what can we say about w to the t? Well, remember that at least it's going to be greater than or equal to the weight of the single individual who performed best. So who is that individual? Or rather, what is their weight at the end? Well, their weight is going to be at least, or in fact, exactly 1/2 to the opt. So this is because every time they make a mistake, their weight drops by a factor of 2, and in total they make optimum number of mistakes, therefore giving this lower bound on the total weight. So that gives us a nice and simple lower bound, very, very simple. Just consider the best expert and see what their weight is going to be. How about the upper bound? The upper bound is a little bit more difficult. It's not as clear to see perhaps, but it's the following. We can actually say that the weight of the total weight is going to be less than or equal to 3/4 to the m. Now, why is this? Well, there's sort of, this isn't too hard to see, but it's because at least half of the total weight corresponds to every time we make a mistake. That means that at least half of the total weight corresponds to people who made a mistake, and everyone in that set, their weight is divided by 2. So this kind of, if you want to write it another way, this is equal to like 1/2 plus 1/2 times 1/2 to the m, where this corresponds to the correct experts, the ones who are right, and this one corresponds to the set of people who are wrong, which is why we scale them down by a factor of 2. But okay, either way, there's a missing factor here. This is not just this. This should be this is sort of the total number of rescalings that we have. Every time, the initial weight is going to be rescaled down by a factor of this, and we start with the original weight being n, because everyone's initial weight is going to be 1. So total, we have this n here. Cool. So now we have an upper bound and a lower bound on this WT. Let's put them together and see what we get. We get that 1/2 to the opt is less than or equal to n times 3/4 to the m. Let's rearrange that just a little bit. This is not too hard. This gives 4/3 times to the m, which is less than or equal to n to the 2 times opt. All we're going to do now is take logs of both sides. So this gives us that m log 4/3 is less than or equal to log of n plus opt. Here for now we're using the log base 2, and so just dividing both sides by log 4/3, this gives that m is less than or equal to log n. Let me write this the other way so it's familiar. Opt plus log n divided by log of 4/3, which is less than or equal to 2.4 times opt plus log n, sort of as desired. So that's the end of the proof. So again, it's not too bad. It's kind of a neat proof in the sense that you just upper bound this quantity by you upper bound it by the weight of everyone, you lower bound it by the weight of the best expert, and just put it together and it works. This is kind of a common theme, and it's sort of similar to what we're going to do for the next step, which tries to improve this algorithm. Okay, so now we've got some nice ideas here that we've set up. In particular, we multiplicatively reward or penalize experts based on whether they're right or wrong. So we're now going to strengthen and generalize this core idea in order to achieve the polynomial weights algorithm, as it's known. So we're going to generalize the type of setting because this will be useful in other cases as well. Before, so we were focusing on the case where each expert made a prediction. They're either supposed to pick U or D. But now we're going to say that each expert, they can make their own arbitrary decision, whatever they want. They're just going to get penalized for it. So there's going to be, well, what I mean by that is there's going to be some sort of a loss function applied. The adversary, sort of nature of the adversary will no longer reveal either up or down. It'll reveal how much each person, each expert will be penalized for their choice. That's one difference. They're going to, in fact, that's pretty much the only difference. The fact that, yeah, each individual will just incur, each expert will incur some loss depending on what their own choice is. So let me try to be a bit more precise. So there's a sequence of T rounds, is the exact same as before. And each one is like, each one is going to be the following process. We will have that the algorithm, that is, we pick our algorithm, or we pick some expert. So we pick a particular expert who we're going to sort of bank on. And then what's going to happen is that every expert will incur their own loss. So they're going to have some custom loss function at time t for expert I. And then I want to say that the algorithm's loss is going to be L sub A at t, which is equal to the loss experienced by expert I at time t. And I'll point out also that each of these losses is going to be in -1 to 1. So just, we're going to keep the losses bounded. So hopefully that makes sense. Rather than picking, the main difference here is the fact that rather than picking just a strategy up or down, we're now going to pick an expert themselves, and we incur whatever loss we get based on what their action was. And the actions themselves are kind of irrelevant. There's just some custom loss function which is defined by the adversary, who's ever setting the sequence of losses. Okay, and one last piece of notation we're going to say is that the total loss of the algorithm is going to be equal to the following. It's kind of the obvious thing. You just sum up the algorithm's loss over all time steps, and similarly, the loss experienced by the individual expert I is going to be the sum of their losses. And once again, maybe now is going to be a bit different in terms of what the regret is. So the regret, let's just state what the quantity is. This is going to be the quantity L sub A of t, sub t, minus the best expert in hindsight. So this is what our algorithm has to pay, and this is what the best expert, if we just picked one individual, one expert, and stuck with them at the very beginning, that's the sort of regret, the difference between those two terms. And we're trying to minimize it. Okay, so that's the setting. And the algorithm for this case is very similar to the weighted majority algorithm. In particular, we're still going to do what we did before for the weighted majority algorithm, was we reweighted each individual based on how right or wrong whether they were right or wrong. So similarly, if they experience a large loss, what we're going to do is penalize them in a multiplicative sort of fashion. And if they experience a small loss or a negative loss, in fact, a gain, then we'll reward them in some way. So all we do is just like scale people's weights in a very similar way. And we'll see how this works. So here's the algorithm we have right here. So again, it starts off the exact same as before. we set everyone's weight to be 1 to start with. And we let the total weight be equal to the sum of the individual weights. So the difference here is in this line. This is probably the biggest change in the whole algorithm. Basically, instead of picking, whoever has the largest weight, now we're going to do a randomized choice. So we randomly pick an expert, where we pick an expert with probability proportional to their weight. So this naturally makes sense. If somebody has incurred a large weight, then you're more likely to pick them. If they've made a lot of mistakes in the past or a lot of losses in the past, then their weight will be very low, and you're not likely to pick them. But yeah, there's a key difference that there's a that this is a randomized algorithm. And as you can see, that the update, similarly what we do as before, before we multiply each person's weight by 1/2, this time we multiplied by this rather arcane looking parameter. We set it 1 minus some gamma times this the loss function of the individual. So this looks a bit weird, but it's kind of necessary for the analysis to work out. And we'll figure out more later about how exactly to set this odd parameter gamma in order to get a good solution. So this is the algorithm. We're not actually going to analyze this form of the algorithm because we're going to try to make a step back towards this query type setting, which we started in the first part. But yeah, this is sort of like how maybe the polynomial weights or the multiplicative weights algorithm might often be seen, the multiplicative weights algorithm for experts. And this is the type of guarantee that we will get for this algorithm. So let's parse this a bit. What does it say? So it says for an arbitrary sequence of losses and any expert I, remember we're trying to be competitive with the best expert, but we're saying in fact something, which that implies, this implies that, but it says that the expected loss of the algorithm is going to be upper bounded by the loss of expert I plus some square root t times square root log n. So there's a few things to comment here. First off, now we don't have, it's not how much our algorithm loses, how much the loss of our algorithm is. This time, it's an expected loss. The reason it's an expected loss is because this is a randomized algorithm. All the previous ones were deterministic, so since it's randomized, we're necessarily going to have to, have a random variable here in terms of how much we lose. Now on the right-hand side, we're competitive with any expert. In particular, you can let this be min of I, and then it kind of exactly gives you this guarantee. And then what is the additive term that we lose here? How much is the regret? Well, it's square root of t, where t is again the number of time steps, and the natural log of n, where n is the number of experts. So it kind of makes sense that it should scale with both of these, because if you have a lot of different options, you can't really hope to learn instantly who's the good one or who's the bad one. And this is interesting because this is square root t. This is kind of this is conveniently a lower order term in some sense. What do I mean by that? If these losses are between -1 and 1, then generally, if you incur a constant loss at each step and there's t time steps, then overall you'd expect sort of these terms to be something like, theta of t. So you can see with this type of perspective, where we picture, maybe the best loss is going to be on the order of t, this is going to be a much, much smaller, it's like the square root of that. So this is really quite miraculous that it's possible to get such a small regret, which only depends on square root of the number of time steps. Okay. So this is how, like I said, the algorithm is most commonly stated, but we're actually going to shift our perspective a bit to a slightly different perspective, which will be more helpful for solving the original problem, which we set out to solve in this lecture, which is the multiplicative weights to private multiplicative weights algorithm for answering linear queries. So in particular, we're going to think about, instead of thinking about, we randomly pick an expert with some probability. Instead, what we're going to do is we're going to imagine that our algorithm picks a distribution over experts. So rather than sort of making a hard decision here and saying like, okay, we're going to pick a single expert with this probability, what we're going to do is be okay with it and say, In fact, I'm not just picking one expert, I'm picking this distribution over experts. It's going to be fractionally picking the first expert, fractionally picking the second expert, and together they make a distribution of experts. And then we'll measure the loss compared with the best distribution over experts if we just fixed it. So this might seem kind of arcane. Why is this? Well, let me explain. Think of the game rock, paper, scissors. There's not going to be any single one expert. If you consider your strategies in rock, paper, scissors to be rock, paper, scissors, then no single expert of these three will be the best one. Really, if you want to win at rock, paper, scissors, the thing you have to do is choose randomly. So therefore, it's natural, for example, to pick the distribution over experts being 1/3, 1/3, 1/3. And that's kind of the loss is measured with respect to that. So that is the intuition, at least, right, that we're not going to just pick a single individual anymore. We're going to define a distribution over experts, and we'll incur loss sort of proportional to how much we invested in each of these experts. But yeah, clearly, kind of like from this rock, paper example, the rock, paper, scissors example, randomization is kind of key to this type of thing. And the distributional phrasing is perhaps the right one. Okay, so let me rephrase using this new perspective. So let's write sort of, we set the setting here, and let's revisit the setting and say it as follows. So again, we have a sequence of T rounds. And in each round, now the algorithm will choose not just an individual, a single expert, but they will choose a distribution P to the T over the experts. They kind of choose how much they're going to bank on each individual expert. And then the algorithm experiences how much loss? Well, like I said, they'll experience loss L sub A to the T, which is equal to the inner product of the loss vector at time t dot product with e to the t. So what does this mean? Essentially, we're saying that, okay, if you invested however much in, let me just write this out, I guess. E to the t sub I, L sub I to the t. So the idea is however much you invested or how much you sort of weight you put on individual I, then you incur loss proportional to whatever their loss is. Yeah, it's kind of natural. And you just to sort of relate this back to the previous case. In particular, the algorithm is allowed to pick a distribution which is just a single point mass. So they could, for example, choose P to the T to be 1 on element 1 and 0 everywhere else, and that would essentially simulate choosing expert 1 in the previous thing. And you can see the loss function works out the same way. So this kind of rephrasing is only a little bit, you can potentially think of it as a bit more general than before. But they're both equivalent if you consider, this loss versus, the expected loss. They're really just the same thing. So, okay, with this rephrasing of it, where the algorithm chooses a distribution every time and experiences the loss based on, the inner product of the distribution and the loss vector, we can rewrite the algorithm above as follows. I guess I was going to write that here. But okay, the algorithm is the following one, which is, the same, call it polynomial weights algorithm, but it's the sort of distributional phrasing. So what is it? Initially, we start with the uniform distribution. That is, all of the experts sort of have an equal weight on them, or each of the domain elements have an equal weight on them. And at each time step, we do the following. We find the normalizing factor, how much we would have to divide these weights by to make it into a distribution. And then we select the distribution P sub T to have, weight proportional to its probability proportional to its weight. And then what we do at each time step is, again, do this update where we update the weight of individual or expert I based on this multiplicative rule, which still should perhaps seem a little bit arcane, but really just convince yourself that this is kind of a multiplicative update. In particular, like, if this is a large loss, say L sub I to the T is equal to 1 or something, then you can see that we're scaling down the individual's weight, and if it's negative, then we're scaling up their weight. But yeah, this is almost exactly the same thing as the algorithm above. I just changed a few words here. Instead of selecting an expert with whatever probability, we're just going to select the distribution to be equal to that. And here's the guarantee for this algorithm, which is kind of it's very similar to the one we had before. It's just sort of phrased in terms of these distributions. So let's take a look at here you saw that it was just equal to this capital L, which is the sum over all time steps before. But now we're going to explicitly write it out as a sum. So what type of guarantee can we say here? We can say that we have the guarantee that the sum of the inner product of, essentially the loss attained by the algorithm, if we sum it over all t time steps from 1 to t, then this is going to be upper bounded by the sum of the loss of any fixed distribution, that we could have possibly had. So if you just fix some distribution, some strategy overall, some randomized strategy over the experts, then you can be competitive with that, plus again the same 2 times square root t square root log n. And this is again a very nice bound because it's very minimal in terms of the additional cost here. So yeah, we'll see how to prove this now. So the proof is actually very similar to the one we had above, the one we had where we were we were looking at where there's a best expert and we were just trying to reweight things by factor 1/2. So all we're going to do is the same type of thing. We're going to take a look at this quantity W sup t, and we are going to track how this evolves over time. In particular, we're going to upper bound it by kind of some upper bound on the total weight of everyone, and we are going to lower bound it by the weight of the kind of the best distribution over things. So yeah, so the proof again, we're going to upper bound and lower bound on W sup t. So how do we do this? Well, what is the what is the quantity? W sup t is equal to the sum over all the sum over all individuals at that time. All the experts. And so we're going to upper bound and lower bound this in 2 ways. So the first thing we're going to do is we're going to upper bound. The first thing we can do is see how this update will correspond to an update on the overall weight of everyone. So this tells us how each individual's weight changes, but what does that imply about how the total weight changes over time? How can we write the total weight at time t plus 1 in terms of the total weight at time t? So we can do it as follows. This is just going to be the sum of the updates, essentially. And, I want to write this in terms of W sup t, just because we want this to be a sort of recursive formula. And just sort of factoring this the right way, you can just write this as W sup t times 1 minus, actually, this very nice expression we had, actually, L sup t dot E sup t. Yeah. Perhaps times a gamma. Yeah, sorry, there's a gamma missing in the notes, which I'll correct. And how did we do this? Well, we just basically, looked at this sum. Noting that in particular, this P sup t is equal to you know, the vector which is defined by wi divided by capital WT, you can just sort of, if you factor that out, then you'll see that it's exactly equal to this. Okay, so now look at this. This is just sort of unrolling one t here. So we can just do that iteratively. And if you unroll this all the way down to w1, then what we're going to get is the following. We have that w sup t plus 1 is equal to w1. Well, I'll just write this out actually. W1 is going to be just n because everyone's weight starts with 1 times the product of these updates. 1 minus gamma times L to the T dot E to the T. And this is the product over all time steps, T equals 1 to T. Okay, what we're going to do now is we're going to take the log of both sides, and we're going to use the following inequality, which is rather helpful. We've already seen some things like it, but we're going to use the fact that ln of 1 minus x is less than or equal to minus x. So using both of these facts on this expression here, we have that ln of w sup t plus 1 is equal to the ln of n. And then we do it on this this term here. The product, we can pull it out and it becomes the sum. So summation of t equals 1 to t. ln of 1 minus gamma L to the T dot P to the T. And now we will use this inequality I mentioned here, which is, so this makes it less than or equal to ln of n minus gamma times the summation of L to the T dot E to the T. So now this might actually start looking kind of nice, in fact. So this is where we're going to conclude with the upper bound. Then we're going to do the lower bound. But to show you that we're kind of on the right track, notice the fact that we have the summation of LT PT, which is exactly what we were going for here. So that's actually going to be where that term comes from. And this ln of n kind of corresponds to this term, though you might not see it yet. We'll get to that. Cool. So that's the upper bound on this. Let me just write that sort of succinctly here, just because we're going to use it later. ln of w sup t plus 1 is less than or equal to ln of n minus gamma summation over time steps of L t dot e to the t. This is going to be one key inequality we're going to use. Let's do the other one. We're going to do the lower bound. So what are we going to do? We're going to consider any. So we're going to fix some expert I. So by that I mean we're just going to look at we're going to prove a lower bound in terms of any single expert I. And then that in turn will imply a bound in terms of any distribution over those experts. So yeah, this might seem a bit weird, but let's just try writing something down and see what happens. So what we're going to say is that the natural log of w t plus 1, this is going to be greater than or equal to like the same trick we did before. The weight of overall is going to be greater than or equal to the weight of any individual one. So we're just going to say, consider expert I, take what the log of their weight is. Then this can be written as the following summation. This is just essentially doing writing this out in terms of its updates. So it starts at 1 and it'll be updated in the following way each time. From overall time steps. And now what we're going to do is use this very handy inequality. Not the same one as before, but a sort of similar type of one here. So, sorry, I didn't explain where both of these came from, but you can derive them without too much trouble using a Taylor expansion. And this holds for 1/2 less than or equal to x less than or equal to 1/2, minus 1/2. So I'll comment that this does impose some sort of restriction on gamma, but it's fine because we're going to pick gamma to be, like this anyway. But okay, so this is one inequality which we'll find useful, in particular right about now. This lets us say that this is greater than or equal to minus gamma times L sub I of t minus gamma squared times t. Yeah, and that's just basically by, just writing this out. Cool. Okay, so in particular, since this holds for any individual expert, then, sorry, let's write the inequality right here. So note that this holds for any individual expert here. So what we can do is actually take a, this also holds if we took any sort of mixture over, over experts as well. Therefore, if you kind of just, replace this w sub I to the t plus 1 with sort of like taking the inner product with respect to a distribution, kind of like replacing this by, inner product of p dot w sup t plus 1, doing the same sort of thing, then this lets you derive essentially the same thing, except you can write this as with sort of the inner product with probabilities, and that'll give you something like the following. You can then show that, this is like minus gamma times the inner product of p times L sub I to the t minus gamma squared times t. The reason why there's no dot product or anything here is just because of the fact that since we're taking a convex combination over these inequalities, we're just summing pi. Oh, sorry, this should be there's no I here just because it's a dot product of something which has all the i's already implicit in it. For this one, we're just going to be summing over pi for I equals 1 to n. So like that'll just sum up to a 1. So this would just be a factor of 1, so we're not going to write it here when we do this convex combination trick. But overall, this will give us the following. We can say that this is equal to minus gamma times, break this into the summation over the different times. Summation of t equals 1 to t of p inner product of L sub I to the lowercase t minus gamma squared times capital T. So, okay, this is actually, and this is, sorry, what I want to say, this is less than or equal to ln of w sup t plus 1. So this is the key inequality that we want. Again, the nice thing to note here is note that we once again have this inner product of p and the losses, and this time it's sort of any p, including, say, the best p that would minimize it. So, okay, we've got these two inequalities, the two bounds on w to the t plus 1, or rather the natural log of it. And let's just put it together. This lower bound, sorry, this upper bound on ln of wt, and this lower bound. If we put those together, let me just write it as one big inequality, putting those two terms together, and then we can see what we can do with it. So this is the lower bound. And we know that this is less than or equal to ln w of t plus 1. And this is less than or equal to ln minus this gamma times the summation. Yeah, I guess we don't have this I here either. Okay, so putting these two together and rearranging it, then what do we get? Let me take this step by step just so you see all the steps. Just moving that over. then we will move this over to the right-hand side. And then we have these two other terms here, plus gamma squared t plus ln of n. Now what we're going to do is we are going to do two things. I'll do these at the same time because neither of them is very complicated. We're going to, one, divide by gamma. And we're also going to set gamma to be equal to 1 over square root of, sorry, not that. We're going to set it to be, let me write here. It's going to be set to be equal to ln of n divided by t, square root of ln over t. So if you just do this and you do these two operations here, then it's not too hard to see you get the following regret bound. So you can see here that this is like in comparison to the best in hindsight, the best single distribution in hindsight. And then these two terms sort of will be balanced and combine to be equal to, what is it? It'll be equal to 2 square root ln of n divided by t. Wait, sorry, is that the scaling that we used? Sorry, no, it's going to be t times ln of n. And that completes the proof. So let's just, maybe this was a bit arcane and you might be wondering where I came up with this gamma. Well, the reason is because, it's a parameter which I wanted to balance out these two terms here. This term here, if you set gamma squared to be to the t plus, ln of n, you set those two to be equal to each other because these are both going to be additive costs. Then you get that, dividing by t, and taking the square root gives, this term of gamma. Cool. So that was a lot of math. It wasn't really too bad though, because it was very simple once you knew what you were doing. Like all you had to do was upper bound and lower bound and then push some symbols around. But we got this very nice algorithm here, which allows us to somehow, almost miraculously, pick a sequence of distributions, which will, approximate the single best distribution in hindsight in terms of minimizing the losses, plus some kind of lower order error. And this is the multiplicative weights framework. This is very powerful by just like considering the right sets of losses, and it can give you good answers in a lot of different cases. So there's many there's good sources of many different applications of this. One place I'd recommend is the sort of survey of Aurora, Hazan, and Calais. They have a very nice article, which I've linked in the notes, talking about the multiplicative weights meta algorithm and all of its applications. So I'd recommend that if you care more. But we're going to talk in the next and final part of this lecture about how to use this for the original problem we started with, the private multiplicative weights algorithm.